Yeah, so hi, my name's Jorge. I have two last names, so I always get called Jorge Ortiz, which is fine. I prefer Jorge Ramirez. In fact, on my high school graduation T-shirt, I was listed as Ortiz first name, Ramirez last name. So all Hispanic people who understand the pain of having two last names, that's the story. Okay, so the name of my talk is "So You Want to Talk to a Qubit." The idea I had was kind of introducing anyone who comes to the talk to the world of experimentalism. So we deal with things that actually exist, unlike the theory people who always talk about these weird spin thingies and Lie algebras and whatever. So if you hear any digs at theory people, it's totally personal. I have a lot of friends who are theory and they're smarter than me. That's why. Okay, so you want to talk to a qubit, and the subtitle I think is also really important because it's a bit of an obvious thing to say, but it's not obvious when you're working in a lab. But really, you are working as the measurement person, us, and you're fighting against the universe. And the unfortunate fact is that you are also part of the universe. So there's a lot of experimental parameters that you need to take care of and things like that, which I'll talk about in this talk. But first, I wanted to introduce myself. So I'm now starting my third year as a physics graduate student. I'm Latino identifying, and my pronouns are he, him. And I think an important part of my identity is that I was an illegal immigrant or undocumented immigrant, because at the age of like 9 months old, I decided that the economic situation in Central America was untenable. And so I overstayed a tourist visa. I was very smart, 9 months old. So I ended up getting my papers in 2018, and my undergrad I did at the University of Maryland. I accidentally grew up next to a really, really good school for physics. So that was great. A bit of my background with experimentalism. So I graduated high school in 2017, which was only a couple of years ago. Don't lie to me. I had a project where I randomly met a University of Maryland professor, friend of a friend of a friend. And through chance, we ended up doing an internship together, and he basically coached me on how to be curious about the natural world. And so what I did was you'll see like this is a really janky setup, like really, really, it's like a high school level. But it was fun. What I did was I attached an accelerometer to a bridge. It was really sketchy watching a kid with like a bunch of cables connecting something to a bridge. I was very nervous. But anyway, I attached an accelerometer to a bridge, and I measured like the oscillations in the bridge as people walked. I did a Fourier transform, even though I had no idea what a Fourier transform was, and I could see all the resolved peaks of like the different frequencies. In 2018, I started college, a physics major from the beginning. I ended up landing an internship because of my counselor, who I told I really want to do experiments. This is what I'm going to do, and if you could help me, that'd be great. So they got me a summer internship where they actually paid me. It was nice. It turns out they paid me to inhale lots of solder fumes. I was soldering several hours a day because they were part of the LHC collaboration, and they were focused on upgrading the data handling and the voltage regulation of the LHCb detector specifically. So they did a lot of things with us undergrads. The main thing was the soldering, and eventually it turns out that one of the grad students or postdocs or something messed up one of the like PCB design schematics, and these were like 30 to 40 layer PCBs. They were really, really crazy complicated because they were designed to handle gigabytes per second of data, at the LHC. So they had us like find variables in like one of like 6 PDFs and like trace them through to make sure the names matched on either end. So that was interesting times. But I think it was a great experience, and I can't stress enough how important it is to at least find something related to, okay, I said experiments, but it could be theory, whatever those guys do in undergrad. Because of my two research experiences in high school and a freshman/sophomore, I ended up applying for the NSF REUs, which I really, really think you need to apply to them every summer. Like they're so good for your resume and I guess your development as a person. I spent the summer of 2018 at Caltech. I worked with LIGO. It sounds really cool. What I was doing was like plugging numbers into Python, but I learned a lot of things on the side. And interestingly enough, a lot of the math overlaps with what I'm doing today. So you'll see here is a picture or a GIF of, yes, GIF, of two rotating large massive objects. I think the intention is for these to be two neutron stars. They could also be black holes. But the point is that they're so dense and moving so quickly that they make these waves in space-time. And so when we see our detector, whether it's an LIGO or another collaboration like I think Virgin or something like that in Italy is what it's called. But you can see like the change in whether the wave is perfectly or whether the wave is like lining up with either of the interferometer arms. You can see the difference in that pattern. So that's a preview of the kind of math we'll be talking about today. It was a great time, but there was a lot of imposter syndrome from having a PI who was kind of a jerk and then having a lot of people around me who were Ivy Leaguers. Still a little bit left over, but I think it was a net positive. So then finally, I had another REU, which I did virtually because of the whole pandemic thing that happened. I had been accepted to 2 different REUs, and I turned one of them down for the other, and then the one that I had turned down canceled because of COVID. The one that I accepted also canceled because of COVID. And I was like, oh, this really sucks. And then my original mentor that I had been talking to like every once in a while, the one that I talked about from high school, he connected me with one of his colleagues who was doing this like virtual REU. And it was both really, really helpful and really, really weird because I was coding differential equations in HTML and JavaScript. And that is as awful as it sounds. It was an experience. But the cool thing about it in the end was like I had like this 100 variable differential equations that I modeled, and you could see like the actual heart ECGs. And then you could see them how they evolve in time. And I got to see how they interact with different tissues in the heart. And then the important part was seeing how this interacts with like different parts of the heart. So you'll see this is related to chaos theory, which is why it had the word physics on it. Otherwise, it was like electrocardiology or something. Okay, so talking about the current time, graduate school. I had to apply to graduate school over the pandemic, which really sucked because I was broke, and I was like, yeah, I'm really cool. I'm gonna apply to a lot of like really, really fancy schools. So I applied to MIT and a couple other ones. They all rejected me, which was kind of sucked. But I did have an interview with MIT. Did not work out because our 1 hour allotted time, he cut it short by to like 30 minutes. And he spent those 30 minutes asking about my like DEI and stuff that I was doing. Like I was just working on this YouTube channel with interviews with Hispanic physicists and stuff like that. So he was really interested. Then he cut it short. I never heard back. So I was like, whatever. I ended up having to choose between UMD and CU, but neither school didn't have any funds officially. But the way that it works really in the most basic of terms for grad school is that the school has a lot of really capable candidates. And so their goal is to find the candidates who A, fund themselves with like some kind of fellowship or some kind of grant, and then B, look like they're going to have the most likely probability of actually completing their PhD, which is extremely subjective. And so the important part was that I did not have an exception. I was not accepted to UMD, but I had a professor who would take me into his lab. So that would have gotten me in, like, no questions asked. And then CU, they had a lot of students who were very well, qualified, but they had a visiting, the visiting fair. I attended, okay, it was virtual, it's a long story, but I ended up talking to one of the professors, and the day after the visiting fair, turns out I got accepted immediately. And I was like, that's weird. And I found out in hindsight that the professor I had a conversation with in that virtual like visiting fair or whatever you want to call it, he was on my hiring committee. So I don't know if it was like correlated, but that was really, really interesting. Okay, so now we're here talking about the thing that everyone's here for, qubits. So physics with an exclamation mark. We love it. So I wanted to outline kind of the talk. I'm first going to talk about learning the language of qubits. Then I'm going to explain how to get your message to the qubit. Finally, I'm going to talk about what interpreting the message you get back from a qubit. And then I'm going to finish with a day in my life as a graduate student. So I like this theme of like just talking to a qubit as metaphorical as it is, because I mean, you really need to separate all these different steps because they are really important and actually very different in your approach and your understanding in order to kind of not necessarily master, but become proficient at doing experiments with qubits. So to start off, language of qubits. I have to do this. I think I like get sick talking about how the difference between a qubit and a bit is, but I think it's really important to understand as much as pop science loves to talk about the difference. But okay, so before we talk about qubits, I'm going to explain to you what a bit is. So you can think of a classical bit, classical meaning not quantum in this simple context. I can say that, okay, I have a ground state and I have an excited state. Sorry, using quantum terms. I have a 0 and I have a 1, whether it means on or off, whether it means up or down. I guess you can kind of think of this as like my blue dot is on the lower half or the upper half. That's the only information I can store inside a classical bit. On the other hand, a quantum bit kind of lives on the surface of a sphere. So the idea is that not only can I talk about my position as like, am I in the bottom or am I on the top, a 0 or a 1, I can also talk about a proportion between the two, the 0 and 1. So we're just looking at the vertical axis here. So I can be anywhere on this ring and say like, oh, like I'm half 0 and I'm half 1. Or weirdly enough, I can say I'm 0 plus 1, so I'll be on this side, or I'm 0 minus 1, and I'm on this side. And those are completely different quantum states. And then, adding another layer of dimension to it, I talked about how it can be 0 plus 1 or 0 minus 1. Well, those coefficients that go in front of the 0 and the 1, they can be complex numbers. Whatever that means, let's just take it on faith that it makes sense, okay? Because otherwise, I'll never get to the rest of my talk. I would love to talk about it. But anyway, the horizontal axis kind of describes the ratio of the complex part of that 0 plus 1. So 0 plus I1. Now, I have a quick slide to show that later. So the north and south poles describe what is known as a T1. So a T1 explains like, okay, if I put my state in the 1, I give it some energy, how long will it take for it to go back to the ground state? Because we all know physics loves to go from higher energy to lower energy in general. And then I had to, for completeness, explain what the T2 is. T2 explains like if I generate some kind of quantum state on the equator, the universe is going to try and mess that up so we can't tell where it is anymore. The T2 explains how long I can kind of distinguish where I am on the equator. There's like a small tidbit that T2 technically only matters for multiple qubits. I put like 3 asterisks because it's really complicated in the sense that someone will love to argue or it doesn't, but in this case, it's fine. So to explain what I mean by that coefficients, if I have a quantum state that is in the 0, I would place it up here. This is where my quantum state is, at the 0. And subsequently, my excited state, you can describe these stars as arrows, vectors, whatever you want. So I have the origin going up to the 0. I have my ground state. I have my origin going down to the 1 state. That's my excited state. Now, if I were to talk about any kind of 0 plus 1 or 0 minus 1, which we would refer to as the superposition, another pop science term, I'm essentially saying that, okay, I'm both 0 plus 1 here. So I have like this equal probability because the coefficients are the same. I have an equal probability to go 1 or 0 when I measure. Because I can only measure real numbers. I can't measure a complex number. And then the whole complex thing is, okay, well, if I'm on this side, right, I start to rotate on the equator, well, I'm still equal probability between 0 and 1. But now I've rotated to this side because I have a complex coefficient in front of my second term. And again, for completeness, you could talk about the opposite side, just 0 minus I1. And then another slide about T1 versus T2, I said like, okay, I started my 1. I can have a certain amount of time before I drop to the 0. And that's kind of what my T1 is. And again, in my T2, I have the universe constantly trying to introduce noise and move my arrow around against my will. So my T2 describes how long I can distinguish where I am on the equator. Okay, classical bits. I used to think, and I said this last week, it turns out that CDs do not have magnets in them. CDs are apparently just holes with different lengths, and that's how they kind of put information on them. I feel like a historian, like I'm explaining floppy disks or something, but that's kind of the idea here. So classical bits, you can talk about zeros and ones. We do in information theory or whatever, but You can use whatever classical system you want to talk about classical bits. So you can use capacitors in a computer or transistors. You can say that if it has a charge, I can call that my 1, my energized state. And if it does not have a charge, I'll call that my 0, my uncharged state. Or in another example, like a CD or a DVD, if I have one of these longer holes, I can have a 1. Or if I have a shorter hole, I have a 0. So the language really does translate. And there is a lot of mathematics between classical and quantum information theory that does overlap. It's really cool, but not the focus of this topic. So what physical things can we use for quantum states? Well, we have electron orbitals, for example. We can have an electron spinning around some atom or some nucleus, protons, neutrons, whatever. And if my magnetic field from my proton is pointing down versus pointing up, I can call that my 0 and my 1 state. Josephson junctions are actually what superconducting qubits are made out of, which I'm realizing now I didn't say that's what I focus on, but I focus on superconducting qubits. These Josephson junctions have a superconductor with some insulator and then another superconductor. You essentially talk about the probability of electrons tunneling through or not. And whether or not an electron has tunneled through, you call that a 1 or a 0. And then finally, you have trapped ions. Trapped whatevers. You can do photons in cavities. You can do neutral atoms or whatever inside I don't actually know how they trap neutral atoms, but the ions are really simple. They just put them in an electric field, right? I just totally generalize an entire field of physics, but you just put them in electric fields. Okay, so discussion questions. What does it mean to have noise in my measurement? We're going to talk about measurements next, but if I were to take say a voltmeter, right, and I have some certain amount of noise, what does that mean? Is it possible to change the amount of noise that I have? Well, is there things that I can do in order to minimize my noise? And then finally, where does this noise come from? So maybe the simplest example would be to talk about doing a voltage measurement. So let's all discuss amongst each other, introduce yourself to your neighbor, no need to be shy. Just talk about, like, if I measure a voltage, what kind of noise I have, and just talk about the discussion questions. All right, Mr. Theorist. What's noise in your voltage measurement? Tell me. What? Tell me what the answer to the questions are.
What is it?
You tell me.
What is it? Measurement?
Yeah.
Is it called in my head?
I'm sorry. I didn't realize it was.
They only had the cheese for it. Or Hawaiian.
Hawaiian, the city, the city is really common.
Yeah. Yeah. I got it from the beef.
You know, I'm always there. That's my next discussion. How'd you know they need so many? Every single one.
And I thought I would get better.
You can just say you need to learn how to swim. You don't have to be like.
But here's the lesson is like, oh yeah, let's drop it in the water. And the girl was like, yeah, I think you're doing good. Yeah, I won't say the whole way.
Okay, so does anyone want to share their answers for the first one? Let's talk about what does it mean to have noise in a measurement? Does anyone have an idea? There's a lot of conversations. So I was hoping that it was about like this. So no, okay, so I'll help a little bit, okay? I could think of a voltage noise as some volunteer.
We were talking about like exactly like voltage meter, like there's only a certain amount of digits that you can read, and that's some sort of units. Or like you said, if you're getting different measurements each time, and then like I was saying, just other sources that your detector or whatever it is picks up that can allow the signal.
Awesome. Yeah, no, that's a great example. Yeah. So for anyone who didn't hear, he was talking about how you have voltage noises, or voltage noise can come from like, okay, you only have a certain amount of digits on your screen, which is directly related to like the precision of your instrument. You also talk about you can put your experiment somewhere where it's isolated because there are other sources besides the one that you're interested in that may be affecting your measurement. And yeah, I think those are great answers. Does anyone else want to answer the questions? That's okay. I can talk too. I love talking. Okay, cool. So, from my perspective, what does it mean to have noise in a measurement? Like, I understand that I'm an experimentalist and I'm part of the universe. So I'm trying to measure something else that is in the same universe. So the perspective that I have is, okay, I need to measure the thing that I want to measure and either cancel out or remove other things that I don't want to measure. So for the example of the LHC, that's a perfect example. They have a lot of different things they can do to minimize this noise. So you could do it actively. For example, you can actively put your detector somewhere where there are less sources. So, miles underground, for example, or there's the neutrino experiment that is at Fermilab that shoots neutrons through the Earth's crust to a gold mine that's, I don't remember how far, how your partner, how far deep is the gold mine where they detect the neutrinos that your partner works at? He doesn't know. He's a terrible partner. Okay, so I think it's like miles or kilometers, but it's like really deep underground. So any cosmic rays that come in do not make it to the detector they have. Is it possible to change the amount of noise by the way you measure something? So like I said, you have the ability to measure things of the universe that you are a part of, but you're also part of the universe. So as weird as that sounds, the idea is that, okay, the way that I measure matters a lot, because if I measure something, by definition, I have to disturb it. So by disturbing it, I get information out of it, but now it's been changed. So I can measure very strongly, but I really can't rely on it being the same afterwards. Or I could measure very weakly, and by weakly measuring it, it doesn't change that much, but I, as a result, get less information. So that's kind of hinting towards a bit of measurement theory and quantum mechanics, where I measure something, there's like this, uncertainty principle that talks about, or really alludes to the fact that there's always trade-offs. There's always some kind of pair of conjugate variables. Finally, we kind of briefly talked about where does the noise come from, but any other source, it really depends on what your experiment is. So the biggest obstacle to me as a quantum experimentalist, how do I communicate with my qubit without introducing noise from the environment? I thought to separate it in terms of avoidable and unavoidable. And I crossed out avoidable because nothing's really fully removable. But some unavoidable noises in a quantum experiment is noise from your environment. So someone turned on the microwave and your detector picks up a big signal. Or noise from your measurement devices, you're using a multimeter from the 90s because you're part of a physics 1 lab, Who knows what the accuracy of that thing is? Potentially avoidable. These are the ones that I have to deal with quite a bit. So I can reduce the noise that I introduce from my wires because of the thermal noise. So my wires exist in room temperature. I will not myself go in the vacuum. I keep the vacuum over there where the qubit is. I'm at room temperature. My wires pick up thermal noise, right? Because everything has moving atoms. I can reduce that by introducing attenuators into my measurement setup. Vacuum fluctuations, I thought was an interesting way to talk about it because it's a bit more of an advanced concept, but instead of allowing the vacuum fluctuations to affect your measurement that much, you can shift what variable you're measuring. And this is a little really hand wavy, but let's just skip that one. It's not super light. Let's just move this one over here. Okay, so then the one I think is really funny is how well do you know your parameters? Because I can say that in a serious way or I can joke about it. The joking part is I have very, very often, and probably today, for those of you who are watching my screen before the talk started, I changed some wiring and now my experiment doesn't work. It could be as simple as I forgot to turn on a power amplifier or something. I don't know. But the point is that like I am saying my qubit is 4.7 gigahertz and my resonator is 7.1 gigahertz. And I put those numbers into my experiment and I have them do the measurements, right? Are those numbers correct? How accurate are they? Is it possible for them to be correct? Or can I only ever be within some certain distance? These are all questions that you kind of ponder when talking about quantum information measurements. And then the bonus points that if you're a big nerd, you're a theorist, you would think about like there's intrinsic quantum uncertainties, right? The uncertainty principle, the one that everyone gets on their t-shirt or whatever, the pop science one, it's like you have uncertainty in two variables can always or must always be greater than a certain value, h bar over 2. The idea is that, okay, if I'm measuring position and I can like sacrifice some precision in my momentum and I measure precision, but there's always some boundaries. So these intrinsic quantum uncertainties, which that's why I kind of put vacuum fluctuations on this side. That's one of those things that you can't avoid. That's really just the fundamental limit of the universe. So bonus points. All right. Now, everything in physics is either a two-level system or a harmonic oscillator. This is the graduate level. Mostly everyone just says like it's just a harmonic oscillator, but secretly they let you know that everything's also a two-level system. There's also a group of people that like to talk about Lie algebras or these weird, crazy terms, but I don't agree with that. There's just two. Unfortunately, for me, superconducting qubits are both two-level systems and harmonic oscillators. So I can't just specialize in one. I have to do both. It makes my life difficult. So what is a harmonic oscillator? This is the equation, the potential energy of a classic harmonic oscillator. Totally, like when I was an undergrad, I was like, why do I need to know this stuff? I just need to connect cables. It's actually important to know this stuff, unfortunately. But the idea is that if you have a potential energy, the further you disturb from the equilibrium point, the more energy you have. And you can kind of visualize this as a ball rolling down a slope. So my energy is the parabola. It's one half kx squared, and then the 1/2 k, whatever. It's just a coefficient. But the more energy that I have is proportional by x squared, how far away I am. So if I go really high up, I'll come back really quickly down and just overshoot to the other side. And it's harmonic because whatever energy you have, as soon as you let go, you're going to be oscillating back and forth around this equilibrium point. So you can visualize it as a spring. The quantum harmonic oscillator, I felt that it was necessary to include these, but essentially, if I look at this and I say, okay, well, I drop my ball at position 5, I can say with perfect accuracy where it's going to be at time t or x if I just use kinematic equations. But quantum mechanics forbids this, and you're required, depending on what energy you have, right? If you're energy 0, energy 1, 2, 3, and 4, and so on, the amplitude of the wave function describes the probability of your being there when you measure. And these are the steady state solutions. They will oscillate. I maybe will show that after the talk. I have it as an extra slide, but this is just the equivalent of this. For whatever reason, they'll teach you in quantum 1 or 2 if you've not yet taken it. So that was the language of qubits. Now we're going to talk about speaking to qubits, pun intended. So I talked about how you want to keep your environment or the universe from messing with you, as it always does, messing with your measurements. So, we have to filter the inputs, right? Like, how do we make it so that only I can talk to it, but no one else can talk to it, be like really possessive over our device? We use another harmonic oscillator, which I think is funny, but it's actually quite clever. The idea is that if you have two harmonic oscillators, right? You have two harmonic oscillators and they're like coupled by something in the middle, some coupling constant or whatever you want to call it. You can see that they'll start transferring energy between each other. This is kind of like the physical intuitive picture. To speak in a more physicsy way, we have modes between the two harmonic oscillators, and this is just one mode. But this is the mode that we want to use because by doing a specific impulse on one of them, we can say, okay, well, all of the energy is going to be on harmonic oscillator number 1, and then it's going to stop eventually and transfer all of it to number 2. Oh, I put the picture here. This is the one I was going to show you about the quantum harmonic oscillator. So the A and B are the modes, similar to this, but for a single harmonic oscillator. A and B are the modes for a classical one, whereas C, D, E, F, G, H, all of those are just quantum modes, but like oscillating in time. So not going to go into it, but it's super cool. It's on Wikipedia. So, okay, I said we need another harmonic oscillator, but I can't just attach a pendulum to my qubit. As cool as that sounds. We use something called a cavity. You could also call it a resonator. It's another word for harmonic oscillator without the harmonic part. We use superconducting microwave resonators, which is just a lot of buzzwords. But these are the harmonic oscillators that allow us to control how our quantum system, I say communicates with the environment, really just how it sees the environment. Like this is how we, close the world on our qubit relative to our measurements, and we keep them from speaking to anybody else. So resonate, another discussion question. I'll explain why this is relevant in the next slide, but what would happen if I shined a laser between two mirrors? And I think that everyone as a kid tried to do this at some point. I know I did, at the grocery store where they have like the mirrors between the produce or whatever, just trying to see inside and see how many reflections I can see. Maybe I was just a really weird kid, but what would happen if the mirrors were infinitely reflective? If they had a finite reflectivity, and how could this be related to trying to make a filter for some frequency or some kind of system? Let's go ahead and talk for a couple of minutes about that.
So I think you probably right.
All right, bringing it back because we're a little getting close to the end of the talk. So here's an example I found after Googling. Someone took a photo between two mirrors. And you can see like it's really cool. It's going forever as much as you'd expect it would. But the interesting thing about this example is that these are finite reflectivity, okay? This is not the infinite reflectivity like, imagine your cow is a sphere or whatever kind of physics problem. This is the real world. And if you notice, you look a little closely, the darkening of the image kind of leans towards the green part of the spectrum. And this is because the mirrors whatever these mirrors are made out of, that material absorbs every frequency, but it absorbs green a little less. So that's why as there's more and more bounces between the mirrors, more green light survives than anything else. So this is a good example of that. Now, why did I bring up this whole mirror example in the first place? If you have two mirrors and there's a certain distance between them, and I kind of removed the slide that talked about this, but I think it's important. So if you have two mirrors and they have a certain distance between them, there's only a specific wavelength can be allowed between these two mirrors. okay? Because the light has to form a standing mode inside the mirrors. And the standing mode refers to how the light just stays in between. So putting these two mirrors, anything that kind of bounces between two things will form this boundary condition where only specific things are allowed inside. So why is that relevant to microwave resonators? Instead of two mirrors, I promise this is something that kind of looks like two mirrors. What really is happening is this is our the green thing is the chip that you put your qubit on, and then we have superconducting metal right in the center, and then on the outside we have whatever our ground plane is, depending on your geometry. This is definitely not always the case, but this is one example. And so our electric fields that carry our information travel inside these like holes between the two. Now, I put this picture in the beginning, but here it is again. This is exactly what the simplest type of qubit measurement looks like. So you have this thing here is the transmon. It's just another word. It's a slightly more interesting qubit than just a superconducting qubit. The transmon, specifically the xmon, because it looks like an X, it connects and is protected from the outside world by this resonator. And so again, you can kind of think of it as like on one end and on the other end, there's a finite reflectivity, and the length decides exactly what frequencies are allowed to enter. So for those of you who have taken waves, you might think about it a little more and kind of ask like, okay, well, there's multiple frequencies that can fit inside, like multiples of n or whatever. This is true, and that is specifically engineered so that, okay, well, our resonator might be 7 gigahertz. That means that our modes for this mirror cavity might be 7, and then 14, 21, and so on. And we don't really care about those because we put our qubit below at like 4 gigahertz. So, and then there's also like, okay, well, there's a finite reflectivity. The simplest way to think about that, okay, well, if there's a finite reflectivity, I lose some of my signal every time it bounces. But another more kind of difficult for me, at least, to understand is that, well, if the more imperfect my mirrors are, the more frequencies like around the resonant frequency it starts to allow to enter. And so that's a little hard for me to wrap my head around. So I have a picture of that towards the end of some data that I took. Again, so we have this picture of our CPWs, which are effectively like the wires. So that's these trenches here. My signal travels from, this is me right here, the input, and this is also me here, the output. I send a signal through, and whatever frequency of signal I send through, if it matches the frequency of my resonator, it'll, instead of coming back to me, it'll go in. So essentially, I'm measuring whether I see a signal or not. And then finally, there's this extra piece right here. This is just a way for me to say, okay, I want to put my qubit in the ground state, or I want to put my qubit in the excited state. However fancy that needs to be, it could just be I blast it with an electromagnetic waves, or like I send really fancy pulses. That's the whole point, because it would be difficult to send 4 gigahertz through a 7 gigahertz resonant frequency resonator. And this is kind of what I mean about the imperfection of the mirrors. The reason why they're not perfect is because my electric fields kind of like, they're not just only limited to the holes in the trenches. They tend to go above into the vacuum. They also tend to go below, which is the real problem. They go into the chip itself. And depending on the type of material, whether it's sapphire or silicon, there are other nasties inside of there, like oxides and something that my lab is interested in, which is TLSs, another acronym. They're just like random two-level systems that we don't want to be there. And the reason why it introduces loss is because all of the atoms inside will be polarized, and that energy used to polarize is energy that I won't get back from my system in the form of information. Okay, so we talked about how to speak to a qubit. We talked about why it's important to have a resonator and what the qubit actually does. Now I'm going to talk about my experimental setup, and this is the last section before I talk about graduate school. So I thought it would be interesting to show some of my personal diagrams that I draw for my lab. They want me to do it in like a really fancy like CAD program where like I actually have, but I like drawing better. I'm a terrible artist, but I can draw shapes because the computer does it for me. But the point being that I can show, okay, well, these are all of these vertical lines represent my inputs and outputs. And then the horizontal lines represent each stage of my refrigerator. So I haven't talked about my refrigerator. I'll show some pictures of it in the coming slides, but the dilution refrigerator is what allows me to do these measurements in the first place. I mentioned earlier that there's such a thing as thermal noise. If I try to measure my qubit at room temperature, well, first of all, it won't be superconducting, but ignoring that problem, there's just too much noise. All the atoms are wiggling everywhere. I can't tell what's going on in my qubit until I I have to go to below like 20 millikelvin. And as an example, helium, which is the material or liquid or whatever you want to call it, that has the lowest boiling point, it's 4 Kelvin. So I have to go like in order of like 200, 300 times. I can't do math. 400 times lower, a lot lower than helium's boiling point. Okay, so I have my inputs and then I have my outputs. And continuing on the other side, you'll see like I have the way that I separate my incoming and outgoing signals with this component here. This is my favorite component. It's just an amplifier that turns, it is literally as perfect. It's like as close you can get to quantum amplification as possible. I didn't make it, I just got it, and it improved my measurements by like a factor of like 300. It's insane. And then finally, this funnel looking thing is the way that my lab can measure 6 devices at a time. It's a cryogenic switch. All it does is kind of flips like little metal poles every time I send a pulse, and it connects or disconnects each device, which is really important because our dilution refrigerator takes like 48 hours to go from cold to warm and 72 hours to go from warm to cold. So as nice as that sounds, because that means I get to do nothing, what it really means is that I don't get to measure, and instead I have to do other boring things like coding or data analysis or things like that, things that are not working in the lab. And I also have this kind of signal flow diagram where my signal in the purple comes up from 23, goes all the way down, goes through my sample, and then comes back, and then I measure it over at 27. And then if I want to measure backwards, because sometimes you care about your forward transmission, sometimes you care about your backwards transmission, I start at 24, go down, do the same thing, but on the other side, and come back up, and I'll measure here. So I can do forwards, I can do backwards. And for those of you who'd like electrical engineering, you could also do reflections. And that can be important at times too. So, okay, my dilution refrigerator. It is a crazy looking thing. It's got copper plated with gold. It's kind of weird to get used to, but I'm just touching gold all day. The idea is that there's stages to it, and then this little vertical slab is where I attach my samples to. So the dilution refrigerator uses helium as a liquid, and helium as a liquid can only go down to 4.1 Kelvin. And so this is important because, well, in the world of, thermal room temperature people, like how do we make something cold? Okay, you just grab some ice, you touch it, right? It's like, okay, now it's getting colder. If you want to be a little smarter, a little bit more interesting about it, you can have a refrigerator, like a compression refrigerator that everyone has, where it's just like pumping and changing volume and PV equals nRT and all that crap. That doesn't get you any lower than like 4 Kelvin because still you have to use a refrigerant and so on. And the best refrigerant you can use is helium. How do you go below 4 Kelvin? It's thermodynamics. What you do is you combine helium-3 and helium-4. And then that, because it's a combination of two different things, one of them acts like I'm starting to go back into the jargon. One of them acts like a fermion, one of them acts like a boson. That's not a theorist. One acts like a fermion, one acts like a boson, and then when you separate them, there's some cooling associated with that. And that is like my ELI 5 or maybe ELI undergrad physics major, how that works. So this sounds like magic. I mean, honestly, it is. But the downside is that I only have like a couple square centimeters, like maybe a dozen square centimeters to attach my samples. And I really can only cool like microwatts. So if you were to put like, a watt of power, this would instantly go back to room temperature. So I can only do like really, really, really low power measurements, which is fine because my qubits are low power. Here's a picture showing the different stages. So if you remember the horizontal lines, we have the 3 Kelvin stage and then the 10 Kelvin stage. And in between, we have a bunch of different electronics. These are the still useful, but not as cool. These are the electron mobility transistor amplifiers. I don't know how they work. I mean, I'm gonna be honest, I just know how to say the acronym, but they mobilize electrons or something, and that makes my signal better. From the 10 to the top of the fridge, this is 10 Kelvin. It's really important to have these stage separations because we can kind of like instead of trying to go from room temperature to 10 millikelvin, we kind of separate it into pieces, and we can control those individually a lot better. And we can spread the cooling power amongst those stages. But we finally get to the top of the dilution refrigerator, and that's where the like the more the components that don't need to be as cold live, but they still contribute to the cooling of the fridge. And so you'll see like that's where these inputs are above the fridge. It's not pictured as where all the inputs and outputs are, but the 50 Kelvin starts here, and then the 10 Kelvin starts here, and then the 3 Kelvin will start here. You'll see those triangles are, so I'm not lying, these triangles are the amplifiers. Finally, this is a picture of where I would actually put my device. You'll see I put my qubit on the top and my resonator on the bottom. It doesn't really matter, but that's what happens. You'll see that I have cables connecting into and coming out of each device. And these cables go back up through a series of very strongly temperature controlled like parts of the fridge, basically. And this is where the bottom half of my diagram is. So you don't see the switch, but actually, if you look really close, you'll see like 6 connectors in like a honeycomb pattern. That's one of the outputs of the switch. These are 2 devices. So specifically, I think it's device number 2 and 5. Those live on this, we call them cold fingers. I always thought it was a really terrible name, but they're called cold fingers. And I even put little pieces of tape to organize them. And yeah, okay. So that's all the experimental part. Everything I talked about in the first and second parts of the talk were about kind of learning what qubits speak, like the language of quantum mechanics, and then also talking about how to control the way you talk to qubits. But all of that has nothing to do with the third part, right? So the third part really talks about like, I didn't put a slide, it's okay. The third part is about actually like interpreting what your qubit is saying. And so I kind of see that as I have to actually code things. I can't just like control the knobs on my instruments. I mean, you could if you really wanted to, and that's how they did it, you know, back in the Stone Age in 2008 or 2012 when they were starting to work with superconducting qubits. But we live in a society now, this is 2024, I write code. I hope no one over the age of 20s or 25 or 30s is listening to this. But the point is that organization is important. I have so many scripts. I have so many things going on. It doesn't help that I have ADHD and like things are just everywhere. But the way that I do things is I have things organized in terms of chronological order. So when I start a measurement, I start with like, okay, where are my resonators? Okay, these are the frequencies of my resonators. Where are my qubits? Okay, these are the frequencies of my qubits. Okay, now I need to know how exactly much power I need to put my qubit into 0 to 1, and so on. And so I have to organize all these. And if you are in the year 2024, you're not using Visual Studio Code, you're either insane or a particle theorist or a physicist who have to use like Vim and stuff. That's terrible. I feel bad for them. But yeah, and I have all my code. I just thought that would be interesting to show. This is a picture of what my chips would look like on the inside. In this case, it's no qubits, just resonators, but my lab really focuses on kind of understanding how the resonators work, because as cool as qubits are, and I'm kind of biased here, I do want to measure qubits more than resonators, but it's important to know how resonators work. So this is a sample where we were kind of comparing a different, like, okay, well, if we put palladium gold on top, and if we don't put palladium gold, like, what will that look like in terms of the performance of my resonators? Okay, so I put this really quick slide here because I've been talking about resonators and cavities, or sorry, qubits and resonators, or qubits and cavities. The way that we tend to think about this in the field is like, okay, we're just going to steal all the math from like people who are doing trapped atoms and stuff. I can imagine that my 2-level system, which is my qubit, lives inside a cavity, which you'll see, you can think of it as mirrors. The way that I can talk to my qubit is by working with the fields inside my cavity. So in terms, I'll be talking about my qubit drive, which refers to how I'm exciting my qubit. And then I'm going to talk about my cavity drive, which is how I'm working with my cavity. And schematically, this is what this would look like. We have, this is not, I just stole this off Google, but the idea is that we have a resonator, and then we have a qubit, and then we have a line connecting to both of them. And so that's how you'll see, like I have 2-level system, and then I'll have my resonator, and then this red G talks about how they talk to each other, and then the kappa and the gamma, we love Greek letters, makes us look smarter. Gamma and kappa talk about the losses associated with each system separated from the other. This picture again, because you can see that exact layout. This is me drawing helpful, little squiggles, right? So I have my frequency of the cavity where I affect like what's going on in the cavity, and then whatever qubit drive I'm using is the one that's affecting the qubit. Very hand wavy. So here's real data. In this measurement, what I did was I looked at my qubit, I looked at my input, I sent a bunch of frequencies, and I looked at the amplitude of what I saw. So what I saw was as I scanned from 5.5 gigahertz to 7.5 gigahertz, I saw that I get like random garbage, but at specific frequencies, my signal disappears completely. So that's my y-axis. It's the magnitude of my signal. Why does the signal disappear? Well, if we remember, I put that somewhere. Okay, whatever. The point is, like, if I send a frequency, only the frequencies that are allowed by the resonator go through. Turns out that if I send a signal that is allowed through, it would rather go to the resonator than go to my output. So that's why the magnitude of my signal drops. This is important because if I zoom in, and I really wish I included a picture of this, but this is the first draft or first iteration of this talk. But if you zoom in on one of these cavities, it looks like a hill. It's not a perfect sharp spike. It's like a hill or like a valley or something. The width of that hill tells me how good of a resonator my resonator is. Like, how selective is it? You'll see that we measure from like on the scale of 2 gigahertz. So 10 to the 9, yeah, 10 to the 9, right? The width of these resonances are on the order of a megahertz, so 10 to the 6. So they're 3 orders of magnitude more selective than the whole range that I'm looking at. Now, how do we actually make this into qubit measurements? Well, this is a plot of the same measurement. So I do a measurement instead of the whole span. I do a measurement of a single resonator. Each horizontal line is one of those spectroscopy measurements. So you'll see it's very high amplitude because on the yellow region, because it's bouncing off. But when it gets to the blue regions, my signal starts to disappear. So the blue regions tell me where my resonator, its frequency is. I can see what frequencies are being eaten up by the cavity. And the interesting thing here is, on the y-axis, I repeat this for different powers. So if I put a really high power signal, my resonant frequency is here, which is being traced by the red line. As I lower the power in my resonator that I'm measuring with, my resonant frequency starts to shift. And that's weird. I mean, if you have 2 mirrors, it shouldn't matter what the amplitude of your wave is, right? Your resonant frequency is a dimensional thing. Your resonant frequency is determined by how many like wavelengths you can fit, right? But here we clearly see that because of the quantum nature of our measurement, once we start getting to the low power regime, the qubit starts to affect the resonator. And so we go back to the idea of this 2 coupled harmonic oscillators. By themselves, they have their own frequencies, very boring. And when you connect them, they start to change each other's frequencies. So you have normal modes and all these differential modes and cool things like that. And this is a direct measurement. This is proof that quantum mechanics is real. Not to brag or anything. Here's a spectroscopy of the qubit, not of the resonator. So what I'm doing here is, if you look back at the example of my 2-level system and the harmonic oscillator, which is a cavity, I am keeping my cavity frequency fixed. So I like to think of it as like my resonant frequency. Sorry, my resonator is like a keyhole, and I can only see inside the keyhole if I'm directly on frequency. So I fix my resonant frequency of my resonator to what its resonant frequency is. So I'm always looking inside. And then I start to change what my qubit frequency is. So essentially, I'm changing my qubit frequency to see when does it change the frequency of my resonator. So this is kind of like a pseudo version of that. I'm pseudo kind of modulating what the proportion of energy between the two is by changing the amplitude inside the resonator. But here I'm directly saying, okay, I'm keeping my cavity fixed. What happens when I change the energy of my qubit? And you'll see that this peak right here is the main peak that tells me this is the frequency that my qubit goes from the excited state, or from the ground state to the excited state. And for those of you who have eyeballs, you can see there's another peak, much sharper, this is actually telling me what my frequency is for the next level of transition. So instead of going from 0 to 1, here I'm going from 0 to 2. And I did lie. I did say that qubits are two-level systems, but unfortunately, there are other energy levels. We just don't like to talk about them. They're not invited to the barbecue. They're, in fact, a big reason as to why superconducting qubits might have a limited lifetime. I put this here again. I don't know why. But then going on, these are the last few minutes of the talk. Now I want to, oh, that's why I'm talking about pi pulses. So if I'm at the 0, right, because I've done nothing, if I'm at 0 and I want to go to my excited state, on the sphere, that's a angle pi rotation. So I'm going from 0, tracing out pi on the vertical axis. We call those pi pulses. And of course, if you want to go to the equator to a superposition state, like, okay, well, instead of going from 0 to 1, what happens if I go halfway? Pi over 2 pulse. So here what happens is at each amplitude, right? So I say I'm going to send a pulse. The stronger the pulse is, the faster I move on the surface of the sphere. So imagine, I like to imagine like an arrow sitting at the ground state. If I like kick it or punch it or something, it's going to go a certain amount of distance. And this is what's showing you, okay, well, if I punch it like nothing, right, it's going to be like here. And then a little more and a little more and a little more and a little more to the point where I get to the lowest possible amplitude. Like, remember the analogy of the keyhole. We're looking through the keyhole. What is the amplitude? It should tell me what my qubit's doing. Well, if I've done nothing to it, I see it perfectly. Or sorry, the other way around. If I've done nothing, I'm looking through the keyhole and I see nothing because the qubit's doing nothing. If I kick it with this amount of amplitude, I suddenly see everything. I see my qubit, it's excited, my frequency's changed. So I know that this is what I need. This amplitude is the amplitude I need to send a pi pulse. And naturally, maybe this one's a little easier to see. For each different power that I send, my optimal pi pulse, this one's inverted because of reasons. It's related to whether you're looking on or off the resonator. You'll see that my pi pulse is here. And then my half pi pulse would be here. So that's how I do that. Well, why would I want to know what pi pulses are? I mean, the reason is because everyone wants to know how long your qubit lives. So if I put it in the excited state, how long on average will it take for it to go back down to the 0 state? Well, why does it matter? If you're trying to do quantum information or quantum computation or something, well, if you put information in, you don't want it to disappear. That's kind of simple, right? There's a bit more nuance to it because sometimes when you have qubits, you might want them to be like memory storage. So I put some information and it never goes away. That's the time that you would want a very high T1. On the other hand, this is a bit more nuanced. If I want to use my qubit as a processor, if I wanted to just do some calculation in some algorithm that some nerd made, what I'll do is I'll put the information there, let the process run, but I want it to be I want it to go back to its ground state quickly, right? Because if I have a really long-lived qubit, I make it do a calculation and it takes forever to go back to the ground state. It's a really bad processing qubit. So that's one of those things I only realized after taking like, I don't know, 7 semesters of quantum or something stupid because I kept failing or whatever. Point being, we can talk about high T1s or low T1s. No one gets impressed when I tell them, yeah, my qubit lives for a microsecond. Like that doesn't impress anybody. So we just talk about high T1s. Right now, I think the record is by Google or someone in like the high, like past like 600 microseconds or something like that. My collaborators at NIST, they can fab qubits at NIST that are like 50 to 100 to 150. And yeah, so that's what you kind of expect out of the superconducting qubit world. Here is a graph of some measurements I did 2 weeks ago. You'll see my qubit here is 91 microsecond average. This one's 57 and this one's 39. They're all supposed to be identical. So that's one of the big problems in our field right now. The fact that we cannot fabricate these qubits to the precision that allows us to have consistent results. How do you get around that? Depends on where you're working. Google, they have a secret recipe that actually, I think it's IBM who has a secret recipe that lets them have like millisecond coherence times. They're not telling anyone what it is. It kind of sucks, but who knows I don't actually know what the variability is, but you can either make a lot of qubits, a chip with lots of qubits that have really long lifetimes and just use the ones that are good. You could also do something different, try and control the fabrication process, but that's a work in progress. So the final, second to last, well, the next measurement I think is optional. It depends on how we feel about the time. But each color is a different qubit on the same device in the same fridge. And you'll see that the averages go from about 40 microseconds to 90 microseconds. And so that's kind of my dilemma right now. The actual secret problem is that the location, so I got these qubits from NIST. NIST measured them about 3 times higher on the worst case and about 2 times higher. So they measured about 150 average. My best was 90 average. So I got to figure out where this factor of 2 is. And that's kind of what's plaguing my life right now. Trying to make my measurement as good, talking to my qubit without disrupting it. That's really my problem right now. It turns out I think that the thermal room, the room temperature noise is getting into my fridge and exciting my qubits besides me. And so I need to be more selective about what I let into my fridge. So I think that's the end of my talk. I got to talk about my life. Yes, I could talk about this, but I think for the sake of time, I'll skip it for now. But the idea is like I can start with ground or excited and then measure it a certain amount of time later. And then depending on if I wait too long, which is on the right-hand side, my qubits will start to decay, even though I know them better. And if I wait too short, I can't tell what's what. So, and then this is an ideal where I maximize for what percentage I am correct out of the different measurements. So as a graduate student, there's a lot of freedom in my life, the hours that I work. I like to make the joke that as a physics graduate student, I get to choose whatever 80 hours of the week I want to work. So that's the job appeal, that's a joke. I think it's more close, 40, 50, 60, depends on how close the deadlines are. But I arrive to work between 8 and 10:30. I like to arrive early if I'm going to leave early, and if I'm going to work late, I like to arrive late. This was kind of BS. I'm supposed to be reading every day. I don't like reading. I like cables and measurements and stuff. But the ideal day is I need to be reading something every morning. My personal productivity hours are from like 10 to 12. That's kind of the time where I'm really into the stride. I got all my things going, and I'm at least likely to turn a device off when I shouldn't be turning it off. And so I really try to focus my important tasks then. Sometime after that, I kind of crash, whether it was because I'm running out of caffeine or running out of Adderall, whatever. That's where I start to have lunch, talk to other grad students, try and copy their experiments, see what they're doing right. And then around 4 to 7, like I said, depending on whether it's an early or a late day, I'll go home, do chores, run errands, or play video games. And then I mentioned that halfway through my second year, I found out I had ADHD, which is a great thing to figure out in the middle of a PhD program. Which makes it really difficult, and it makes it really important for me to follow a kind of structure. And a joke that I make with my psychiatrist is like, well, ADHD is like one of the few mental conditions that we know exactly what the cure is, like drug them. But like also another cure is structure and schedule and consistency. And it turns out that's like the worst mental condition to have when you want to establish some kind of structure or schedule. So it's a battle, and it's one that I'm getting better at, ideally. So that's a realistic day in my life as a graduate student. So thank you, everybody. I appreciate you giving me an hour and 12 minutes of your time and pizza. And thanks again.
All right, so we have time for a few questions for Jorge, but before that, if you have any feedback you'd like to give us, the organizers, or Jorge, please scan that QR code. We really value your feedback. If you look at all that.
These 1,400 students, remember to check in attendance on your Flickr app if you found that so already.
All right, any questions for Jorge?
That means I explained everything perfectly. Oh, I didn't. Okay, just kidding. What's your question?
Once we figure out like noise thing, like how will this and that like?
Yeah. Yeah, that's a fantastic question. It almost feels like a planted question because it was so good. It's a joke. So, I mean, the idea is, well, my lab, I didn't really talk about what my lab is focused on specifically. I just mentioned that we are interested in kind of researching the effects that, or we're just essentially just trying to understand the properties of these superconducting resonators better. so that we can improve the way that we communicate and filter information from our qubits. So what I'm working on right now is kind of the bane of experimentalism. I'm working on cables and measurements and stuff, not actually physics. But the idea is once I have our measurements set up to the point where we can measure these qubits to the same accuracy as other labs, then we can start doing really cool things. For example, can we use qubits as detectors for loss sources inside of the substances that we make our qubits out of? Another thing that my lab mate is working on, well, I talked about the resonators, and I just said, like, what if you send a signal in and then you measure the one coming out? You can do way more complicated things. For example, what if I send a signal in that is purposely split? So instead of sending one signal frequency, I send a frequency with two kind of little brothers that are less in amplitude, but they're slightly off resonant frequency. Well, because they're off frequency, they're going to bounce off, right? But if I am too high up, right, one of them is going to bounce more than the other. And if I'm too far, I'm gesturing with my hands, but that's the best I can do right now. If I'm too far below this resonant frequency, the other one's going to bounce off. This is something that is used at LIGO, actually. They send lasers, split the laser, and then kind of observe the different frequency components. If we understand how to use that method with microwave resonators, then we can really truly say that we know what the resonant frequency of our cavity is at all times. So that's a really big and lofty goal. Kind of the intermediate is saying like, okay, can I use those off resonant frequencies as a sort of like measurement device? Can we say like, what is our performance of our resonator? And that will actually have immediate benefits because right now, if I measure a resonator, it'll take about like 2 hours of measurement time to measure a single resonator, and one device will have up to 8. His quoted time, which we haven't tested yet, but he's quoting that he'll be 100 times faster. So instead of 2 hours per resonator, I'll measure, I hate converting hours to minutes, 120 divided by 100. Well, it'll take 2 minutes almost, like less than that to measure a resonator. So that's immediate impact on the field. So yeah, thanks for the question. That was excellent. Are there any other questions? I would love to take questions about not just my research, but also like grad school, what undergrad was like, anything about anything I've talked about in the talk. So yeah.
I've got a question. Can you go back to
Yeah.
your resonator pictures?
Yes, wherever they are. The one of the real resonator or just in general? This one?
Yeah, so you got some zigzags here because you need the right length.
Yeah.
For your resonator. But why are you zigzagging like this, right? Why not zig farther before you zag?
Oh, I see what you're saying. Yeah, that's a good question. I mean, I've designed a very simple I've designed this kind of thing myself. And there's a lot of like different approaches to design of superconducting qubits, but in general, what you care about is first order, the simplest thing you care about. Is it the right length, right? That's why you do the zigzags. Then the second order, the next most important thing is like, is there some kind of corners? The reason we round them is because we don't want corners. That causes really high electric fields from like, it's a Jacksonian problem. I don't want to talk about it. Corners are bad when it comes to fields. So we want to round them to avoid the corners. And then the next level is like, okay, well, how are my fields going to spill over from my like trenches into the surrounding substrate? I can't really give an like informed answer as to why, like how you would decide the length of the zigzags. But in general, like as long as you get the right length and as long as you don't have any crazy errors, like for example, if this drive were really close to this right here, that would be a big problem because then your drive is leaking into your resonator. But the length of the zigzags itself is kind of like a smaller, less important parameter. Really, it's just about space and design efficiency. You don't want to compact everything too much because then all the fields start to overlap. So it's trial and error, I feel like, at least at my level. You had a question back there. 2 people had questions.
Other than qubit stuff, like computing stuff?
Yeah, totally. I'm biased because I'm okay. We're all physicists. We're all just pretending to be electrical engineers. It's over the EE lab, that's why, or EE department. So using resonators are really interesting because unlike qubits, so qubits, you want to measure them at like single photon levels. resonators, I mean, you could measure them like 100 decibels higher. So like 50 decibels higher. So 10 to the 5 times more energy. So resonators allow you to measure things more easily because of how good of a quality factor they have. So what my lab has done before I joined is use resonators as kind of detectors for errors, any kind of imperfections in the substrate. So in this chip, you can use these resonators like, okay, like if I see some kind of fluctuation in the frequency of my resonator, then there must be some kind of other harmonic oscillator besides my resonator that's connecting to it. And those was what I was referring to as TLSs. So those are considered the biggest obstacle right now to superconducting qubit lifetimes. The fact that we cannot fabricate these chips precisely enough or with enough purity that whatever impurities are left over, whether they're like deposited by the fabrication process or whether they're just natural components of the substrate. For example, when you use silicon, you'll have a bunch of really dirty oxides because you exist in an atmosphere. You have, instead of just silicon, you'll have silicon oxide 1, Si2O5 or whatever. I'm really bad at chemistry, but point being that whatever impurities exist in the chip, you can use the resonators to measure them. And moving forward, right now we're working on an experiment where we're trying to actually characterize that loss. So we made a chip that has 3 nanometers of oxide, 5 nanometers of oxide, and then 15 nanometers of oxide. And we were able to show that the relationship between the loss and the thickness of the oxide was a linear relationship. So that was really interesting. But yeah, that's some of the work that we're doing about the resonators. Was another question back there? Or no?
Let's put it off.
That's true, yeah.
Talk to you after. So let's thank Jorge one more time.
Thank you for having me. Cool, yeah, would love to talk about anything. Have a great evening.